You saw the moon? Which one's the moon?
In the front.
It's in the front, yeah?
It's 500 BC and the world goes dark, but this is not the first time it's happened. The Babylonians were meticulous record keepers and were obsessed with the moon. They were the first to realize that once every 6,586 days, an eclipse happens. All right, so before people jump on me, solar eclipses happen more frequently than once every 18 years, which is the 6,586 days. What this specifically is talking about is called the Saros cycle, which is the exact amount of time it takes for the geometry between the sun, the moon, and the earth to all line up in the same spot again, and then it all repeats, and so it becomes very periodic. And this is what the Babylonians actually discovered. Okay, so I just wanted to clarify that before anybody jumps down in the comments and corrects me. Anyway, let's get back to it. The Babylonians were the first data scientists, and they fit a model to their data. It's a ridiculously simple model, but a model doesn't have to be complicated. It just needs to work. Another great example, again, comes from cosmology, where Johannes Kepler set out to defend Copernican theory, which stated that the planets traveled in circular orbits around the sun. Kepler tried to show that the orbits of the planets can be inscribed and circumscribed about the 5 Platonic solids, which would give more structure to the Copernican model, and the direct connection between the number of known planets and the number of orbits he could produce this way seemed divinely determined. I mean, they didn't know about all the other planets at the time. But no matter what he did, he couldn't get it to work with the available data. He needed to find better data, and the best astronomical data of the period was kept by Tycho Brahe. Tycho Brahe? I'm never sure how to pronounce that. But he built his own observatory. Okay, he got his subjects to build his observatory. With this better data, Kepler realized that he was completely and totally wrong. He did the most painful thing a mathematician could do, and he threw out his model. And then he made a better one. Kepler discovered that the planets don't actually travel in circles, but they travel in ellipses. And he found 2 other rules about their movements as well. These are known as Kepler's laws of planetary motion, and they mystified many scientists at the time. Certainly, they seem to hold up, and better than Ptolemy and Copernicus' theories. But why? Why not a circle? Was there some underlying reason to this? Can we make a model that explains this model? That leads us to Sir Isaac Newton, who solved this simply by inventing calculus and differential equations and physics. And he also did some stuff in optics. He did a lot.
You know, I'm something of a scientist myself.
So he realized that Kepler's laws could be explained with the inverse square law. So that's great. But it sounds like a heck of a lot of work, and a tremendous amount of insight that has to be used to infer anything from these piles and piles of data. And in this present world where we live with big data, we want to be able to do this automatically. And so we wonder, can we teach a computer to do what Isaac Newton did? Or at the very least, what the Babylonians did?
I'm sorry, Dave. I'm afraid I can't do that.
I mean, generally we think, yes, we can. And that's what has led to the whole field of data-driven methods in dynamical systems. However, not everyone agrees with what is the best way to go about this. What I'm going to do is show you 3 different ways to approach this problem. And just know that there are many other ways out there too. And hopefully by the end of it, you'll be able to Newton up some models for yourself. So, first thing is first. We need to select a modeling framework. We could go with a discrete time system or a nonlinear autoregressive system or a differential equation. Let's stick with differential equations for now. Calculus is the natural language of physics, so it seems somewhat natural to stick with it. Now we're going to do a second thing, and we're going to make another assumption about our unknown dynamics, because we want to reduce this problem from being a broad, like find a function that is our dynamics, to a linear algebra problem. What we're going to do is called a parameter identification problem. Now, usually we don't make any crazy assumption about the dynamics, but we are going to assume that it is a polynomial. Polynomials can be used to approximate anything given a high enough degree. So even if our dynamics isn't a polynomial, we hope we can find a polynomial that is still somewhat close. So now the question is, what is our data? Well, the idea is that we're observing some sort of trajectory and we're observing it through time. And just like when you're watching a video on YouTube and, videos usually happen in somewhere between 24 and 30 frames per second, each one of those frames can be thought of as a snapshot. And so here we're going to label our snapshots as, say, x0, x1 up to xn.
And we have our dynamics f as a linear combination of monomials. Now, we know we can get samples of f by taking derivatives of our states. So a naive first approach to the problem is to take numerical derivatives. This would lead us to a system of equations that are linear in the unknown parameters. If we have enough snapshots, then this matrix should be a full column rank, and we can invert it with a more Penrose pseudo-inverse. What this means is that we're going to take that matrix, transpose it, and multiply it on the left, and if we have full column rank, then that means that the matrix transpose times the matrix is a square matrix that is invertible. And if we multiply by the transpose on the other side, then we can just ultimately invert that matrix off of our parameters, and so now we have found them. Now, this doesn't always give great answers, and sometimes we want what is called a parsimonious description of our dynamics. That means as few basis functions being non-zero as possible. One way to approach this is to convert this linear algebra problem into an optimization problem, like this, and then to regularize this optimization problem by adding some positive lambda times the L1 norm of the parameters. The resulting parameters found this way will be mostly zero, and that's actually a feature of L1 regularizations. Now, this is what the Cindy algorithm does from Steve Brunton's group over at the University of Washington, and the paper that introduced this is Discovering Governing Equations from Data by Sparse Identification of Nonlinear Dynamical Systems, and this was published in 2016. Cindy, by the way, stands for the sparse identification of nonlinear dynamics. Now, I mentioned that this might not be the best way to go about the problem, and this is because we are taking numerical derivatives. Numerical derivatives are extremely sensitive to sensor noise, and we'd like to find a way around it. Brunton ameliorates, makes it better, this with a TV regularization. But we can dodge this problem completely by using the fundamental theorem of calculus.
Okay, so this is actually my favorite demonstration of why numerical derivatives are really not the way to go. And it's because you can have a very, very small amount of noise in the actual state, but the derivative noise could be huge. And so if we take a function, say y of t, and we add something like delta times sine of, I think it's t over delta squared. As delta gets very, very small, in magnitude, this is getting very, very tiny. And so you'd have very small perturbation of your actual signal here. And this is your original signal. But then, if you take the derivative, say d dt, then what you end up having is y prime of t. This is the derivative of your signal. This is what you are trying to get with numerical differentiation. But then over here, you have delta times 1 over delta squared times cosine of t over delta squared. And this is equal to y prime of t plus 1 over delta times cosine of t over delta squared. As delta gets closer and closer to 0, you get closer and closer to your signal here. So this is actually converging to your signal. But over here, you still end up having a sort of infinite blowups as delta gets very, very small. So even though you're getting much, much better approximations of the signal, you're getting much worse approximations of the derivative here if you use numerical differentiation or any sort of differentiation technique. And so this is why we moved away from using numerical differentiation and why we want to use numerical integration, because when you numerically integrate this sort of thing, well, this guy is going to be vanishingly small as delta goes to 0. So moving up, gets rid of the noise problem. Moving down makes it a lot worse. Okay, so let's take a look and see what changes when we actually use integration. Really, what we're using in both cases is linearity of differentiation and linearity of integration, and they both lead to linear algebra problems. And so let's just take a look and see what happens. So what I'm going to do is I'm going to take a look at both sides of this, and I have x dot on the left-hand side, and I have these yi x's on the other. If I go ahead and take an integral of both sides, then the fundamental theorem of calculus is going to really come and help me. So I'm going to take the integral from 0 to, say, t of x dot of t dt, and this is going to give me, on the left-hand side, x of capital T minus x of 0. Now, on the right-hand side, I can go ahead and compute these integrals. So I have the sum I equals 1 to m of theta I times the integral from 0 to t of yi of x of t dt. Now, f is unknown, but I have selected these yi's and I just don't know these theta i's. So yi is known, and in general we're going to be expecting that the trajectories have been observed, and so we're going to be using these for numerical integration. So I can numerically integrate this guy. I don't need to numerically integrate this guy because I have the endpoints of my trajectory. There we go. That's our sort of setup. So what we're going to do then is we're going to assume that we have a whole bunch of trajectories. You know, you could have trajectories like this. You could have one really big trajectory, and then each of your other trajectories are going to be longer and longer segments of this guy. And so these could be all different setups you have for your trajectories. It doesn't really matter. So, but in general, I'm going to call these gamma 1, which is going to go from, say, 0 to t1 to rn. Overall, I'm actually going to call these, say, r little m. Do I want little m? I don't want little m. Sure, let's do little m. T little m. Okay. Essentially then what we're going to do is we're going to use each one of these guys as my data, my essential bit of data, and I'm going to make a row for each single one of these guys. And it works out exactly the same way with numerical differentiation, just doing one row at a time and with the same thetas on the other side. So on this side, we're going to have gamma 1 of t1 minus gamma 1 at 0. So if gamma is actually a trajectory in Rm, I can put a transpose here, and once I put this transpose here, if I use the same basis functions for every single dimension, then I can actually turn this so that these guys are just vector valued or n valued weights, and so, or parameters. And so then I can just put these guys as transpose on the other side, and so I'll actually have a matrix of parameters, and it works out really cleanly. Now this is equal to, now we're going to have a whole bunch of integrals from all these guys. And so we're going to have the integral from 0 to t1 of y1 of gamma 1 of t dt, and all the way up to the integral from 0 to t n of ym of gamma 1 of t dt. And this goes all the way up to the integral from 0 to t of capital N of y capital M of gamma n at 0 at t dt. There we go. And this is all times, say, theta 1 transpose, theta 2 transpose, all the way down to theta m transpose. So in one dimension, it's really simple. I mean, you just get, these are all real numbers. In n dimensions, this ends up being a matrix where each column represents each one of your dimensions. And we can only do this if we select the same basis functions for each dimension, which often makes sense as far as a sort of tractability sort of thing. If I didn't do that, I'd have a matrix that is twice as large and it would take a little bit more to compute. And then what you can do is you would have to invert an even larger matrix, which would take even more time. And so if you only have to compute the inverse of this matrix, say you're working on, say, a 13-dimensional system, then this just makes this a 13-column matrix, and this is still the same size matrix as before, and you can still invert it. So anyway, so you can resolve this with the same more pseudo-inverse approach that you would have done before, and so yeah, that's that. And so not really much has changed, except now we have gotten rid of the numerical differentiation and we've traded it for numerical integration, which works a lot better. Now, we can generalize this even further, and we can use sort of like a weak approach to this sort of thing, or we can actually compose these ideas into another function, and we can expand it that way. And this will allow us to even tease out even more information out of a single trajectory. And there's actually a lot of really cool operator theory that goes in behind it, but I'll tell you about that one later. So instead of taking numerical derivatives, we can take a numerical integral. Then we can do the same thing we did earlier and invert this matrix to find the parameters. We can also use the L1 regularization here as well. One additional thing we can do is add a collection of continuously differentiable functions g1 through g capital S and compose them with our trajectories. If we take the time derivative of this composition, we actually get the gradient of gi evaluated at gamma t times
the dynamics. And those dynamics can be expanded just as before. And if we integrate both sides of this, the fundamental theorem of calculus comes into play again. Now we have a generalization of the integral framework, and a selection of different g's allows us to pull different information from our trajectories. And this is the same idea that goes into, say, using feature spaces and using different features when you're looking at all sorts of different data science or problems. And so these g's play the role of our features in the setting.
So I want to make one clarification. So in this video, when I was rewatching this video, I realized I'm saying our weak method, or we decided, or our method, when we're talking about this sort of weak method. And I want to clarify that there's actually more than one weak method. The one I'm talking about, the one I'm presenting to you, is the one that me and my colleagues came up with back in, say, 2018 or so. It was published in the Conference on Decision and Control. This is different than what, say, Messenger and Bortz did. And theirs was published, I posted archive in 2020, I think. And there their approach is different than my approach. And it's interesting that these two separate ones exist to solve more or less the same problem, or at least in one dimension. So Messenger and Bortz, they actually use integration by parts. And this jives really well with things like partial differential equations. And they have a follow-up to PDEs, it also posted in 2020. And our method works more for dynamical systems. And this comes from this sort of like Koopman generator perspective, and basically using a combination of the chain rule and the fundamental theorem of calculus, as opposed to the integration by parts. And so integration by parts, it jives well with PDEs, and it comes from that sort of culture and community. And the way I'm presenting it fits sort of dynamical systems, and yeah, it's just really interesting how these two sort of manifested roughly around the same time, and so and independently. I've now talked to Bortz about it a bit, and you know, but at the time we had no idea about each other. So just want to clarify that, and we can go ahead and get back to get back to the math. All right, and so then what we have is we have g composed of x of t, and we take the time derivative here. If I take the time derivative, I end up getting this. And so I have the chain rule coming into play here. And now instead of just g prime, I have the gradient here because g is corresponding to, say, an Rn function. And so then once I have x dot pop out, I know x dot is equal to f of x. And so then I have f of x of t here. F of x of t can be expanded as the sum of theta I times these yi's. I can use linearity of all these operations to write it out like this. Now, I can integrate both sides, and on the left-hand side, I use the fundamental theorem of calculus again, and so this is what I end up getting. What's happening here is I know g because I selected g. X is something we've measured, and so we can use that here. So I take the endpoints of my x, I put them inside this g I selected, and this is computable. That's easy enough. G again, selected, so I can take its gradient. This is known, and this isn't a numerical differentiation, this is an exact differentiation because I selected g, usually like, say, a Gaussian RBF, or an exponential function, or a polynomial, or something. And so I know how to take its derivative, and now I'm going to take its derivative, and I'm going to multiply it by these yi's, which I know, because, again, these are selected, and all these x of t's, these are things that are measured, and so I can use numerical integration to compute this integral. That's great. So now this has set us up again for another linear algebra routine, which we can set up really quick, and I'll do it like this. All right, and there we go. So we see that we have our g that we selected. This is our smooth function that we're putting our trajectories into. And so we're going to have a difference of the endpoints of the trajectory placed inside of g. And then we're going to do this over and over again up until we have gamma n. So we have gamma 1 through gamma n. We have all of our trajectories here. And over here, it's a lot like we had before. We had y1 and gamma 1 of t, but now we have the gradient of g composed of gamma 1 of t times all that stuff. And then we just do that for all these guys. And so it's more or less the same matrix we saw before. Now, this is all times theta. Now, in this case, it's a little trickier in order to get these thetas stacked as a matrix, and I can talk to you about that a little bit more later. But in general, though, this is more or less the same sort of idea. So potentially larger matrix that you have to invert, but what's nice is that we have two levers that we can pull here. One, we can choose to segment our trajectories in a variety of different ways, and when we do that, that can give us more trajectories to hopefully fill out the rank of this matrix to give us more quality information out of our data. But now we can also use a different G to extract different information from our data. And this is done a lot like what you see in feature representations of data in machine learning. This is a machine learning problem. And so what we could do then is we can have this sort of linear system, which I can write as BG being this vector, MG being this matrix, times theta, which is this, which doesn't change. And we can select a whole bunch of these G's, and so we can have a whole stack like this. So we have, say, BG1 down to BG capital S is equal to MG1 down to MG capital S. And this is all times theta. And so since we have this vector for all the G's that we selected, and we have these matrices that we compute, and then we have this theta, and so then hopefully we can choose as many G's as we need to until we fill out the column rank of this matrix, and then we can use a more Penrose pseudo-inverse and invert this to find theta. So it's nice. So these G's add an extra layer of flexibility to your system, so you might be able to tease out more information out of, say, even just a single trajectory to get at quality information about these thetas.
So that's more or less parameter identification. And it's one of the main ways we do data-driven methods in dynamical systems. It's the way that Newton did as well, where he first identified basis functions such as the inverse square, and later found parameters to match his data. Now, what do you do if you don't have any good guesses at a basis set for f? What do you do then? This is where a regularized regression approach can come into play, and we can use what is called the representer theorem to find the best basis for us. I'll tell you about that in our next installment of this chain of videos. And on that topic, right now I'm actually working on a book on data-driven methods for dynamical systems, and this is going to correspond to one of the chapters in the book. And so I'm going to make a bunch of videos over the next year where I'm going to go into various aspects of this whole idea of data-driven methods in dynamical systems. And if you'd like to learn more about that, go ahead and follow. And I'm doing this in addition to my videos on real analysis, which I'm going to continue to produce. In any case, thank you so much for watching this far, and, well, I hope you have a great day.
Do you see the freckles on the sun? Freckles? Yeah, look, there's on the orange stuff, there's little dots. Look in there. Do you see them? See those little dots?
I think I see 2 dots.
You see 2 dots? Yeah. Those are called sunspots.
I see 2 dots on the wheel.